Howdy, Chem fans! Welcome to one of my favorite lessons of all time, my favorite topics called equilibrium and pickleball. Our target today for day 70 is to be able to explain what equilibrium actually is in terms of a chemical sense, and then to figure out the collision model, this thing called activation energy, and another thing called KEQ, which is pretty darn handy, right? So, of course, today, we would start off today with a beautiful game of pickleball. And if you've never played pickleball, it's one of those friendly games that you can play at any age because it's like tennis, the easy way. There's this little net with little paddles. And you whack it back and forth, right? So what we would do is I'd pull a kid up from class, a volunteer that would just jump into the action, and we'd play some pickleball. And we'd think about that yellow-blue switcheroo demonstration that you would have seen. You hopefully will stop and watch the video if you have not watched the yellow-blue switcheroo video link that I've attached so you understand what we're talking about, the beaker and the magical things it's doing as it goes from yellow to blue. Our job is to figure out what's going on with that. And we're going to use pickleball as an analogy for that because it's pretty darn handy, right? So if we look at these little pickles in the game that they're playing, the key element of this is they have their paddles, but they have the ball, and they can whack that ball, the pickleball, back and forth and back and forth. It is reversible. Well, chemical reactions the same way. So essentially we would set it up like this. We would have me on one side, right, with my paddle and my horrible reflexes, and I would have 3 different pickleballs with me. On the other side of the net, a student would be sitting there, a big hitter. They've got their paddle. They've got absolutely no pickleballs. That would be like a 3-0 ratio, right? Then, of course, I would do what anybody playing pickleball would do. I would hit a ball over to them, and that would change things. Now that other student would have one of the pickleballs, and I'd have 2 of them. But I represent the blue, and I'd have a beaker of blue stuff next to me. I'm like the reactants. The reactants are the blue stuff, and they can turn into the products, the yellow stuff. And that would be the student. So now, of course, there's more blue stuff than there is yellow stuff, so the solution would still look blue. It'd just be a little bit lighter. Then if I continued with my forward reaction, I would hit another ball over to the student. And when I do that, now they'd end up with now they have 2 yellow product balls, and I would have over here, of course, 1 reactant, the blue one, which means that now the ratio, of course, is 1 to 2 of blue to yellow. So the solution would do that magical thing where it changes color and it would turn more yellow. And then, of course, if we continued that, it would turn all yellow. And it does that in the reaction. And then it does a really weird thing. Suddenly it goes from blue to yellow back to blue. But that's because in reality, reactions are reversible. So if we reset it all the way back and eventually they hit those back, we'd end up with all blue. But the cool thing is, at a certain point, we would end up where one person, the blue, and the yellow, the other person, we'd have this nice ratio of 2 to 1. But the neat thing is, as we're doing that, we could continue to hit. And I could hit one over here, and the products could hit one over here. And in the end, the ratio would always stay 2 to 1, even though it was constantly changing. It's constantly changing from reactants to products and from products to reactants. It's just doing it at the same rate. So we are making and breaking yellow and blue at the same rate, but at this magical point called equilibrium, we are making and breaking products and reactants at the same rate, and the concentrations of the reactants and products stay the same. So no matter what, the solution will eventually reach equilibrium and look blue, and there'd still be yellow, and yellow would still be being created. It would just being destroyed at the same rate. And that's essentially what equilibrium is. It's making and breaking the reactants and products at the same rate. So it looks like it's staying the same, but it's constantly changing at the molecular level. And that's how all chemical reactions work. They are all reversible, and they can all reach equilibrium where they are making and breaking at the same rate. Cool. That, of course, is a lot handier with the actual pickleball, but I'll use this FET, which does a beautiful job of explaining it. You should have played around with this FET at the end of the last entry task. And the key thing of this is it's got lots of different modes to use. So first, I'm going to start off with the fact that chemical reactions are collisions. And that means that they're things running into each other. Now, key thing is I can pull this back like a pinball machine. And when I do that, I can unload my reactant and run into the other reactant. And you can see that it doesn't actually react. It doesn't get from the reactant side to the product side of the energy diagram. That's because they didn't have enough energy to break the BC, the other reactant. So if I take that and I reload my launcher and I give them more energy, you can see that green total energy line going in, I can reach the activation energy, that hump. And if I can get over that hump, I can get uphill. And that means, wham, I can turn from reactants to products. And that's an uphill battle to do that. And you'll notice that I can then also turn from products back into reactants, because all reactions are reversible, right? It's all about collisions and having enough energy to actually make or break a bond. And that's what's going on right here, right? Now, in more realistic situations, you wouldn't have just one reactant right into another reactant. You'd have a bunch of them, right? So I designed my own experiment and I set it up. And what I'm going to do is I'm going to pause it and I'm going to put 50 of each of the reactants, A and BC, right? And you can see in the reaction it says A plus BC makes AB plus C, right? These are my reactants, these are my products. And it's reversible, like all reactions. Now, key thing about this is I also set up a bar chart up here to get an idea of what's going on. And you can see there's lots of reactants right now, right? There's absolutely no products. Now, the other thing we can see here is there is total energy, and the energy that's right here is below the reactants line, but it's above the products line, right? And this is telling you their potential energy, how much energy is stored in the system, right? In their part. So if I let this play, you should be able to predict what would happen. Well, reactants and products will collide. And when they collide, you can see they go from being this massive pile of reactants to a bigger pile of products. And you can see over here in the concentrations that it started 50-50, but now there's actually more products and less reactants. And it's kind of shifting back and forth because at this point, it's reached equilibrium. It's making and breaking the products and reactants at relatively the same rate. It's not perfect because there's not enough particles in there. But this definitely likes to make products because, well, that's a downhill battle. It's easier, takes less energy to destroy reactants and make products. It can make the reactants, but it's more work. That's why it favors the products at the end of this reaction, like a lot of exothermic reactions do, downhill battles, right? Now, cool thing about this is I can take and clear my container and use a more important tool that scientists use called a strip chart, right? So if we look at this strip chart, one of the neat things about it is that strip chart gives us the ability to look at how many particles are there. So I'm going to take it, I'm going to pause it, I'm going to throw in 50 and 50, keep the same reaction according to my energy diagram, right? And I'm going to let it play. Now, the strip chart, of course, would at this point show lots of reactants, right? And absolutely no products. But that's going to change because they have a chance to collide and make and break bonds, right? When they do that, one of the cool things is you can see them doing that right here in this strip chart. You can see that there was a lot of reactants, then they became products, and eventually, of course, their lines actually crossed, and now you can see that there's more products on top and less reactants on the bottom, and they've leveled out. And at the point that they level out is pretty cool. It's right there that they level out. So if I take this and I pause this, you can see that here is where it levels out for the first time. That's when they're making and breaking at the same rate. That's when they've reached equilibrium, right? So monkey around with this experiment. You can do beautiful things with it and understand what's going on inside of this vessel, because this is essentially what's going on in the yellow-blue switcheroo. It's making and breaking things. We just can't see them. It looks the same at the end when it reaches equilibrium. It'll look a dark blackish. But the truth is it's really making and breaking and destroying at the same rate at that point. So it's both making and destroying products, even though it looks like it's staying the same. That's the cool thing about equilibrium. It's always changing, but staying at the same concentrations, same rate of reactions back and forth, right? So then the hard part of this. When we come into this, I'm going to ask you on the test, and this is the most important, probably the hardest set of questions I've asked you the whole year. I got these two different reactions, A and B. It tells you what the reactants and products are. Pretty straightforward. It tells you their concentrations, give you an energy diagram. I want you to draw what the strip chart for these reactions would actually look like and give an estimation of the end concentration of the reactants and the products. So this is where you would try to answer it, see if you could do it. You can even play around with the simulation day because we're not in class, and then see if you can do it. And then we'll do it together, right? So pause me, try it on your own, draw it out. This is the most important question of the whole year, explains the whole basic planet. Cool, let's try it together. Let's just focus in on A, right? And anytime I'm trying to solve these things, I should recognize that this is a strip chart. It's showing concentration, and this is looking at it over time. So these are behavior over time graphs, right? Like in history class. It's like everything's connected or something, right? Now, this is the reactants. That's the products. And anytime I think about a reaction, the first thing I think about is energy, right? And this is an energy diagram. It's handy. One of the things I can see here is the forward reaction is what kind of battle? It's an uphill battle. And anybody who rides bikes knows that riding up a hill is lame. Riding down a hill is much, much more fun because it's easier. So this is the downhill, the reverse reaction, because it can go both ways. This downhill is an easier reaction. That means this reaction will favor going in the reverse because it takes less energy to get from products to reactants. In addition, these are my reactants, these are my products. You can see at the start of this reaction, I have a huge pile of reactants and absolutely no products, which makes drawing the strip chart easily because it's telling you that, well, we've got a lot of reactants, right? 100 total, and we've got no products. And then I hit play. And when I hit play, they can start to collide. I know you can't see my hands, but they're colliding, right? If they collide hard enough and at the right angle, because it's the collision model, well, then reactants could turn into products. So what's going to happen? Well, that's going to destroy reactants, and they're going to become products, right? Now, key thing of this, of course, is as they're doing that, they're going to try to reach equilibrium. It's not going to happen right away. They're going to make and break each other until they reach a point where they're making and breaking at the same rate. And, of course, one thing I'll notice is they will look something like this. Now, right here is a crucial moment. Right here, this is where they've reached equilibrium. They are making and breaking at the same rate, right? The concentration is staying relatively the same. It would stay the same if it was a true system. And that's because, of course, it's got only 50 particles of each reactant, so that makes it a little bit more chance. It's almost perfectly the same because they're making and breaking at the same rate. And we can see that it's at equilibrium because the concentration is staying the same, even though they're wavering back and forth because they're constantly changing from reactant to product and back at it, right? Also, I can see that right here, it didn't do it quickly. It took some time. It's a slow reaction to reach equilibrium because of this right here. You can see that the forward reaction has a very, very high activation energy. And a high activation energy means that it's going to be slow for it to do that. That's why it favors at equilibrium. Which way? Well, it's got more reactants than it has products. It's going to favor at equilibrium the forward reaction because it's easier. It's the downhill battle. So that makes it easy to predict what's going to happen, right? So let's dig into B. If we look at B, very different reaction, just looking at the energy diagram. First thing I'm thinking about energy, these are my reactants, these are my products, right? Those are reactants, those are products. Now thinking about the energy right here, I can see something. Which direction is easier? Forward or reverse? Well, this is downhill, and the universe is lazy like us. It's easier. It favors the downhill, so it favors the forward reaction. But I can have the reverse reaction too. It's just easier to do the forward reaction, to turn from reactants to products. At the start of this, I have a huge pile of reactants and once again, no products, which means that the only ones that can collide in the initial part are the reactants. So I'm going to start with a lot of reactants, have absolutely no products, right? And let them start colliding. Now you'll notice a crucial thing. There's no hump here. There's no pickleball net, essentially, which means there's no activation energy required for the forward reaction. It's even easier to do the forward reaction. It's like one side's got a net and the other side doesn't, right? So what that means, of course, is the reactants could turn into the products very, very quickly. And that's why it would be steeper because they would react faster. That, you can see that it definitely favors the product side because it's easier to go there. It's a lot harder to go at that side. It's like a volleyball net, right? So that means at equilibrium, it will start to level off, right? Hey, look, what happened there? It reached equilibrium. It's making and breaking reactants and products at the same rate. But this one, of course, reaches equilibrium faster. And it does that because it takes less activation energy to go back and forth because there's no hump for the actual reactants part. There's no activation energy required to go forward. So this will still favor more products because, of course, the forward is easier. There's less activation energy to do that. So you can see they both end up reaching equilibrium, but at very different points. This one would favor products over reactants because it's a downhill battle in the forward. This one, A, would require, of course, reactants because it's an uphill battle in the forward, and it always favors whichever side is downhill. It's easier to set a house on fire and just watch it burn than it is to build it. Things tend to decay over time, like our bodies, because eventually they reach equilibrium, right? Cool. Now, if you understand that, you could dig into C, and C is the bonus round. So pause it right now, write down the question, draw the energy diagram, etc., and try to draw a concentration versus time graph. That would show that you understand what's going on. Pause me so I can imagine that I'm not talking anymore. Sweet. That would be a nice change, huh? Water. Cool. If we go at this together, first thing I always think about is energy, right? Here you can see on your energy diagram that I can see this is my reactants, this is my products. Which direction is easier? Neither. It's just as easy to get from reactants as it is to products, so this would favor neither because both of them have a very high activation energy, an equal activation energy, right? So if we look at this, if you can't get that activation energy over that, then you can't have a reaction. However, this total energy line, the green line, tells you that there's enough energy in the system. The particles are moving fast enough because heat energy is the thing that can affect that to cause it to actually change and shift that reaction, right? So a key thing about this is I can get from reactants to products just as easy, right? And this is the story. If we look at this, this is kind of like ultimate pickleball. The net's not down here. Instead, the net is like a volleyball net, and you got to hit it over. It's pretty hard to get back and forth. The net is essentially what the activation energy is. It's the amount of energy it takes to get to the other side, right? So if I look at my reactants and products, I can see at the start of this reaction, I have, in this time, absolutely no reactants and lots of products. So who's going to collide the most? Well, that would be the one that you have a lot of, the products. It would start high. The reactants would be at 0. Then I can see, of course, they're going to want to reach equilibrium. They're going to want to make and break at the same rate. But are they going to do it quickly? Well, that all comes down to how easy it is to get to the other side. And I can see the activation energy is high, so it's going to take a long time, right? Now, as it starts to destroy products to make reactants, and reactants start breaking into products as well, they eventually will reach equilibrium. And which side is easier? Well, neither. They are equal in their difficulty. So they actually start to overlap each other. So the reactants and the products create this beautiful ribbon where they're going back and forth until they, of course, level out at about the same concentration of about 25 and 25 of each of the reactants, right? And the products. The cool thing is right here where it levels off, this is where they reach equilibrium. It's called the equilibrium point, right? That's when they're making and breaking at the same rate. The forward and the reverse are doing that. You can see that, of course, equilibrium here takes more time. It takes more time on the chart to do that because it requires more activation energy, right? Which means it's harder to reach that. And more activation energy is going to require more time. This one, of course, you can see from the products and the reactants favors equal amounts of the products and the reactants at equilibrium because it's just as easy. There's the same amount of energy for each, which is a pretty rare reaction, but it's good for learning from, right? Also, we can notice that net is the activation energy. It's basically how hard they have to collide to react. So if they collide, of course, the A could run into the BC, and if it has enough energy, well, then it can make and break BC and turn it into AB, etc., right? If it doesn't, then it just bounces off each other. The net, the activation energy, tells you how much energy it takes to do that and how stable their bonds are. If you're understanding that, that's a really, really good sign. If not, you should go into the FET and play around with it a bit. We'll also use it for other things coming up. And you should be able to draw a strip chart for the pickleball, right? So if we think about the pickleball in terms of reactants and products, right? Here's basically what I had. I had a concentration over time. I wish you could see the demo in class. You would start off with a lot of blue reactant and no yellow product. And it would be like 3 of these and 0 of those, right? And then what would happen is it would change over time because we can hit it back and forth in it's pickleball, so there's a small net. In fact, we wouldn't even have a net class. So that eventually what it will do is it will ribbon back and forth, and that would be there'd be a little bit of yellow extra, a little bit of blue, and then there'd be more blue and more yellow, so that what you're seeing is what there's more of. It would turn from yellow to blue, back to yellow, until eventually, of course, it would reach an equilibrium where there was, well, about 2 blues for every 1 yellow, and that's when it reaches that magical point of making and breaking at the same rate. It's equilibrium. Now that's a simplified version of it with yellow balls. If we look at the actual reaction, what it's doing is it's using iodate, IO3, and iodine, 1 minus. The yellow stuff is the iodate. The blue stuff would be the iodine that's freed up as an ion dissociated. And what they're doing is they're going from yellow to blue to yellow to blue. And your eyes, of course, are seeing what there's more concentration of it, the yellow-blue switcheroo, until eventually it reaches an equilibrium. It basically runs out of oxygen, and then it'll lock up and turn a dark, dark bluish-black color as the oxygen, of course, the iodine binds to the starch. But essentially, it's pickleball until they're making and breaking at the same rate. And you can always tell when they reach equilibrium because their concentrations stay the same, even though they are making and breaking at the same rate, right? They're always changing but staying the same. That's essentially equilibrium, right? Dynamic equilibrium, how everything in the universe runs. Now, FET and the intro to the equilibrium worksheet, that's on my website. You don't have to do it for Covito Loca, but I would highly suggest you check out the FET and try it out. You're going to have to download it. Some people it won't work for, but try it out because it's awesome. Now, you're going to get out your notes because there's some other stuff that we got to know, right? If we dig into this, there's this thing called what's going to happen, determining what will happen at equilibrium, EQ. So the way that we do that is simple. First, we write an equilibrium expression, which is simpler than it sounds. It's the ratio of the concentration of the products to reactants. We know lots of ratios. We've been using them like crazy, right? So write down this really weird reaction. Notice that the coefficients are little letters and the actual chemicals would be the big letters, right? As you write that down, this is what we turn in for an equilibrium expression called a KEQ, a constant at equilibrium. What we do, of course, we put the products on top. The brackets mean a concentration of each chemical, and then the coefficients become powers, exponents. So essentially, this would be rewritten like this. With C to the C power times D to the D power is over A to the A power and B to the B power, right? What I've done here is, of course, the brackets is a fast way to write concentration. It means moles per liter, so you don't have to write the units because we all know you love doing that. The key thing is when you do this, remember that only concentrations go in there, not just moles per liter. Also, you can see that basically the idea is this. You take the products over the reactants. And when you're doing it, the concentration of gases and aqueous solutions are the only things that are written. Solids and liquids don't because their concentrations don't change. They're pure substances. But gases and aqueous solutions can change their concentrations, so they go into a KEQ. Also notice that the concentration of pure solids and liquids don't because they're essentially would be one. They stay the same, right? But always remember that it's the pile of products over the pile of reactants at equilibrium. That's the KEQ, right? It's when it's making and breaking at the same rate. I always just think about the products, and that tells me what's going to happen. Now, try writing these, right? Write down the reactions, the equations, and then try to turn those bad boys into KEQs, equilibrium expressions is the long term for it. So we got some nitrogen gas, some hydrogen gas. They're making ammonia gas. It changed the world, but we'll talk about that later. This is what it would look like as a KEQ. I got my products squared over my reactants. There's the N squared to the 1 power. You don't write the ones. And there's hydrogen to the 3rd power, right? Notice they're all gases, so I can write them all in. If I look at the next one, I got barium chloride plus sodium sulfate. Makes some barium sulfate solid, a precipitation reaction, and some knuckle, right? Some sodium chloride. So I always remember, I put my products over my reactants. There's my sodium chloride, there's my barium chloride, and there's my sodium sulfate. You can see that, oh, is that right? No, I got a problem. This would need to, of course, be squared because you always have to check your coefficients. There's twice as much of that stuff, so it has a bigger role in the KEQ. Might be asking yourself, okay, why didn't I write barium sulfate? Because it's a solid. I only write gases and aqueous solutions because solids, their concentration stays the same. Ooh, that's the easy part. Now, what does KEQ mean? This is my favorite part of this. Really, it's just the products over the reactants. If the KEQ is big, meaning that it's bigger than 1, right? It's a big number. 1 is a big number. then there are more products at equilibrium, because that means that the top is bigger. There's more products. If it's small, which means it's less than 1, anything less than 1 is a big number, or a little number, then there are more reactants at equilibrium. Makes sense, because that would mean there's a bigger pile of reactants and a smaller pile of products. That's why it's less than 1. If it is near 1 or at 1, which is pretty rare, that means that there are equal amounts of reactants and products at equilibrium. And if you think about this in terms of piles, it makes complete sense. If I have a bigger pile of products when they're making and breaking at the same rate, that tells me this reaction favors making products, and it would have a KEQ bigger than 1. Hey, that must be a downhill battle because it likes to make products, right? So you can figure out the energy diagrams too. Now, one step further on to this, which will really help you next week, is this. Write down the question. This is how we use it as a tool to predict the future. So I've got some carbon monoxide. I'm smacking it into, colliding it with hydrogen gas. It can make and break this stuff called methanol. That's how you make fuel, right? Glass ETD. I want you to calculate the KEQ if the concentration at equilibrium, that's crucial, it's at equilibrium, of the carbon monoxide is this, the methanol is this, and the hydrogen gas is this. And then tell me what the KEQ means. What does it tell you, right? So pause it, try it, then we'll try it again. Cool. If we look at this, first thing you do is you write the equilibrium expression. That's easy. You basically put the products of the reactants, and the coefficients become the powers. They're all gases, so they all go in, right? Then you use your numbers, check. They're all molarities. Always double check. Hey, that's moles per liter. I can use those. So you plug in the numbers. There's my concentration for methanol. There's my concentrations for carbon monoxide and hydrogen gas, and that one's squared. Then you solve the bottom, you solve the top, and you divide separately. And then if you're smart, you'd calculate it in, write it all out, and get siggy with it. There's, well, 2 siggy figgies. So it's about 590 with the KEQ, right? Now, what does that mean? That is a big KEQ. It's much bigger than 1. So what does that tell us? That means that this thing favors more products when it's at equilibrium, when it's reached its magical balancing point. So it favors the forward reaction. Essentially, it's a big number. So that means that there's going to be 590 times as much products as there is reactants. This thing is definitely a downhill battle. It really likes to destroy the reactants and turn them into products because it's easy to do that. That's why there's a huge pile of them. It's much harder to get back the other way. So always be thinking about energy, right? Cool. Now, normally go into the EQ sheet and try a nice challenge problem, but our target today was to be able to explain equilibrium. And equilibrium is just when you're making and breaking at the same rate, the reactants and the products. You can have more reactants or more products. That's all depends on the energy, but it's all about making and breaking them at the same rate. Think of pickleball, whacking the ball back and forth at the same speed so that the concentrations stay the same. You can always tell when it's reached equilibrium because the concentrations will stay the same, right? That's why the graphs level off. The collision model is simply telling us how much energy it takes for them to collide. Reactions are collisions, and they can make and break back and forth. The activation energy tells you how easy it is to go there. The universe favors going downhill. So that's how we can tell that this would, of course, favor making less products at equilibrium because, of course, it's an uphill battle. It favors going the downhill, but it can do both. And then KEQ is simply looking at the ratio at equilibrium of the products to the reactants. If it's a ratio of 1, that means, of course, that it likes making both. And that's pretty rare, right? If there's a lot of products, that's a pretty good sign. You're going downhill because it's easier to make the products. If it's less than that, it likes making reactants. So you could guess what the KEQ would be for this and the KEQ for this one. But we'll see if you can do that next week. Keeps getting curious there, chem nerds. All right, catch you later.